This is the Wheatstone bridge experiment. And we are in the procedure session. So first step is to measure and record all the resistance used for this experiment. They are R1, R2, R3, R4, which is the potentiometer. The nominal value is 1K, but most likely the actual number is less than that. And then we have a load resistor that's 470 ohm. So make sure measure the actual resistance for all these 5 resistors and then put them here. After that, we are ready to work on our circuit. So step 2, we're gonna build the Wheatstone bridge circuit as shown in figure 3 here. R1, R2, and also R3 with the pot R4. I have already built a circuit as shown here. This is the R1, which is 100 ohm resistor. That's the brown black. And then we have R2, 150. This is R3, 330 ohm resistor. And this is the 1 kilo ohm potentiometer. And I have also set up our power source. We need a 10 volt source. As you can see, this has been calibrated. The power source, the DC power supply, supplies a 10 volt. We are ready to conduct our experiment. And we continue reading here. Construct the Wheatstone bridge circuit as shown in figure 3. R4 should be set to the maximum resistance. So let's crank this up. We need to increase the resistance to its maximum. If you're uncertain, so we're gonna disconnect our calibrated voltage source first, and we are going to measure the resistance of the potentiometer. As you know, when we measure the resistance, we need to disconnect that from the circuit, and then we measure the resistance here. Since this experiment, we only need to use the variable feature of the potentiometer, we just need to use 2 wires of it, and one of the wire is the middle cable. So let's disconnect the potentiometer from the circuit. We're gonna change here to resistance mode and measure its resistance. Make sure we crank this up to its maximum resistance. So far it is 0.87 and then kilo ohm. It's supposed to be 1K, and we already know most likely it won't reach to the expected number 1K. We already learned that from previous experiments that for most potentiometer, although we crank this up to the maximum position, and then we cannot get the expected resistance. This one supposed to be 1K, but we only get 0.87K. Let's disconnect that from the meter and then put it back to the circuit here. Great. Now let's continue reading. This is a quite complex experiment, and I have already computed the steps. So for this experiment, I'm going to show our members the steps for getting the computed values. First, if you read the instruction here, use the voltage divider rule to compute the voltage at point A, and then with respect to the ground, from A to ground. And then we need to get the voltage at point B refers to ground. So let's work on one at a time. VA. So we see the source here connect to this branch, and the source connect to the second branch. Both branches are in parallel. So we're gonna work on one branch at a time. The branch contains point A to find the VA. We can use a voltage divider formula. The total voltage across the entire branch is the source voltage 10 volt. So use VS times the resistor voltage we are interested, which is VA across R2. So we use R2 divided by the sum of both resistors, that is R1 plus R2. Plug in the numbers. 10 volt times 150 ohm over 100 ohm plus 150 ohms. Here I just omit a unit because they will cancel out anyway. And after calculating the number is 6 volt at point A. And I also fill in the entry there, VA equal to 6 volts. And now let's move to point B. Point B is, for point B, voltage B, we used the same method to get it, voltage divider. Still the entire branch get 10 volt. And here, VB is the voltage across resistor R4, the 1K part. So the formula will be Vs times R4 divided by the total resistance of this second branch. That is R3 plus R4, 330 ohm plus 1 kilo ohm. After computing the number is 7.52 volts at here. So I enter VB equal to 7.52 volts. Let's also get the Thevenin resistance. So the Thevenin resistance on the left-hand side can be obtained by shorting the source. So we're gonna replace the source by a wire. No more source, just a straight line, a wire. And as you can see, one side of R1 connect to here, the wire, all the way to the other side of R2. And this side of R2 and that side of R1 also connect together. Therefore, R1, R2 are in parallel. We're going to use the parallel resistor formula to find the total resistance called RTH, Thevenin resistance of the left side of the circuit. The formula for the two parallel resistor total resistance formula is this: R1 times R2 divided by R1 plus R2. Plug in the number, I get 60 ohms. Therefore, this part of the Thevenin resistance is 60 ohm. And then we apply the same method, find the other side of the Thevenin resistance. Again, short the source, R3 and the 1K part, R4 are in parallel. Use the parallel formula, 330 ohms, and multiply 1 kilo ohm divided by 330 ohm plus 1K ohm, we get 248.12 ohms. That is here. After that, we need to use these values to get the equivalent Thevenin circuit. So VTH is computed by adding VTH and the VTH prime. So how about let's plug that number here first. So here I plug in these numbers. VTH, that's the 6 volts, and the VTH prime is the 7.52 volt, which is VB. And then we have RTH 60 ohm, and the RTH prime is the 248 ohms. Now let's do the measurements. So first, I'm going to connect the source to our pre-built circuit. Change here to voltage mode. So now our voltage source provides the 10 volt to this circuit. The wire over here, that jumper, is used to measure the voltage between the points. Okay, so let's see. Make sure we measure VA and also VB. After that, we're gonna enter the measured VA and VB over here, these two entries. So let's do it. We take our multimeter, change to the voltage mode, and let's measure VA first. VA is this point, and then respect it to ground. So this is the ground. We get a 6.02 volt. So let's write it down. Therefore, VA, the measured VA equal to 6.02 volt. Let's measure VB. VB is similar from this point respected to ground. The ground, all the points along the line, even here, that's ground. They all connected together. And I get a 7.32 volts. The calculated number is 7.52 because potentiometer number we use 1K. But as you see earlier, the actual potentiometer value we got is 0.87K. There is a discrepancy here. So I put VB equal to 7.32 volt. Next, we're gonna measure RTH and R prime TH. To measure RTH, first of all, let's disconnect our meter. We also need to disconnect our source. So let's disconnect the source. We need to short the source. So we're gonna use a jumper, connect here to the other side, the ground. No more source. Instead, is replaced by a jumper wire. And now we're gonna measure the resistance between the terminals. So we're gonna measure the resistance from point A. Let's move this aside. And then we measure the resistance from point A and respect it to ground, this side of the circuit. So here I use the 200 ohm range, and the resistance I get is 58.9, close to 59 ohms, but I put 58.9 ohms. So that's the resistance for this part of the circuit. Measure between A and the ground with source shorted. So the expected number is 60 ohm, but we get a 58.9 ohm, pretty close. Now we're gonna measure from here, point B to ground. What we need to do is just to disconnect the red probe and then connect that here. This resistance is higher. We measured that should be over 200 ohms. Therefore, we need to use the proper range. Let's use the 2000 ohm range. So this is equal to 240, 239, or 240 kilo. And if you move the decimal point 3 times, remove the kilo, it's about 239 ohms. So we get a 239 ohms, which is quite close to 248. Again, the same reason we get a discrepancy, because the value we calculated here, but the potentiometer's value we calculated here, we used the 1 kilo ohm instead of the actual 1.87 kilo ohms. So next, Let's continue reading. We already computed 7 ohm resistance on the left side of the bridge in figure 3 by manually replacing the source by the jumper or VC jumper. We get a RTH and a R prime TH. We complete step 4. And step 5, we need to draw the load resistor between A and B terminals in figure 4. So let's go to figure 4. This is figure 4. We have already entered the numbers here, such as VTH is the 6 volt, RTH is the 60 ohm, and then we have the R prime TH, that's the 248 ohm. We have the V prime TH, that's the 7.52 volts. Now we're gonna put a resistor here. That's the load resistor. So I put a resistor here. This is the RL, the load resistor, and it is 470 ohms. We're gonna merge these resistors and the sources since we need to use the superposition theorem. But let's continue reading here. Use the superposition theorem to compute the expected voltage drop VL across the load resistor, and then enter the computed voltage drop in table 2. Then we're going to place the load resistor across terminal A and B of the bridge circuit and measure the load voltage V1. If the measured value does not agree with the computed value, recheck your work and enter the measured V1 in table 2. This requires one more step and it is kind of hidden. So first we need to use the information and then build our Thevenin circuit. As you can see, the first source 1, provides 6 volt this way, clockwise direction. And then the second source, V prime TH, provided 7.52 volt but the other way, in counterclockwise direction. Therefore, they cancel out. The overall Thevenin voltage, I still call it VTH, but this is the overall, is this, and then subtract that. Because again, this pushing the electron this way, the other source pushing the electron the other way, opposite direction. They counter-react or cancel part of the power and the voltage. So we use 6 volt minus 7.52 volt. The difference is negative 1.52 volt, that direction. And then we need to add a resistance. We are not gonna subtract resistance, no such thing. We're gonna add resistance. So 60 ohm plus 248 ohm equal to 308.12 ohm. Actually, this is 248.12 ohm. So roughly 308 ohm or 308.12 ohm. And then we're gonna include the load resistor, RL equal to 470 ohm. And then we use the voltage divider formula to compute the voltage across the RL, this point to that point, the voltage across these 2 points. So the voltage divider formula is the total source voltage minus 1.52 volt times RL divided by the total resistance, RTH plus RL. Plug in all the values. We have the VTH minus 1.52 volt times 470 divided by 308.12 ohm plus the 470 ohm. And I use calculator, I get negative 0.918 volt. This is the voltage across the load. And I enter these numbers into here. So the measured or computed load voltage VL equal to negative 0.918 volt. And afterward, we need to measure that. So I will reset the circuit by disconnecting the meter first. Remove the jumper. And then connect the source back. The red to red. And then the ground to ground. Great. The circuit has been reset. We are going to measure the voltage, so change the meter to the voltage mode. And we are going to do one more thing, that is by connecting the load resistor. I put a 470 ohm load resistor here. So we're gonna disconnect that, connect this resistor, or put the resistor across the two terminals, or connect that to the two terminals. Okay, so we are going to take the probes of the multimeter and measure the voltage from point A, that's VA, to point B, VB. It equals to negative 0.794 volt. And our computed voltage is negative 0.918 volt. That is acceptable. Again, same reason, mainly due to the potentiometer's inaccurate value. So I get negative 0.794 volt. Great. Now we complete the first part of the experiment. We complete up to here. Place the load resistor across the terminal A and B of the bridge circuit in figure 3 and measure the load voltage V1. If the measured value does not agree with the computed value, recheck your work. Enter the measured V1 in table 2. And now we complete the first part of the experiment, which is here. Draw the load resistor between the terminals A and B in the circuit of figure 4. Show the value of the measured resistance of RL. Use the superposition theorem to compute the expected voltage drop, that's the VL, across the load resistor, and enter the compute voltage drop in the table 2. We just did it. We just complete the first part of the experiment up to step 6. So we just place the load resistor across the terminal A and B of the bridge circuit and measure the load voltage called the VL. If the measured value does not agree with the computed value, recheck your work. Enter the measured VL in table 2. We just did it, and that equals to negative 0.793 volt, which is here, negative 0.794 or 93 volt. We are ready to move to the last part of the experiment. So step 7, monitor the voltage across the load resistor. Currently equals to negative 0.793 volt. And we need to carefully adjust the pot R4 until the voltage equals to 0 volt, which is the bridge is balanced. When the bridge is balanced, remove the load resistor and measure the voltage from A to ground and the voltage from B to ground. So let's do it. First of all, take or grab our potentiometer, reduce the resistance until this equals to 0. Perfect. So I get a 0.00 volt, which is 0 volt. Now, let's see. So the balance of the Wheatstone bridge circuit has been achieved. Remove the load resistor. So this is the load. We are going to remove the load. Actually, we don't need the meter probes now. Let's also disconnect the probe temporarily. And then we also need to disconnect the load resistor. Afterward, we need to measure VA. VA is measured from this point, either here or there, they're connected, refer to ground. So connect here, and then to ground, there. Change here to voltage mode, and then use proper range. I'm using the 20 volt range. It can measure up to 20 volt. So VA equal to 6.02 volt. So let's write it down. So VA equal to 6.02 volt. We just measure the voltage from A to ground. So let's do the same thing for voltage from B to ground. So we disconnect that. We don't need to disconnect the ground probe. And then we measure point B to ground. So from point B to ground, we get the same voltage. That's 6.01 volt. And this makes sense. Voltage B, VB equal to the same voltage, 6.02 volt. That makes sense because the Wheatstone bridge is balanced. That means the voltage across AB, the voltage between point A, point B, terminals AB equals to 0 volt. This is called a balanced Wheatstone bridge. There's no potential difference between the terminals. Since the load resistor has been removed, these measurements represent the Thevenin voltage of the balanced bridge. Enter these measured voltages on figure 5. And then replace the voltage source with the short. Next step, we're gonna replace the voltage source with a short. That means disconnect that for now, disconnect here temporarily, disconnect the source. We don't need the source anymore. From here to the other side to ground. So we just replace the voltage source with a short. With the short in place, measure the resistance from point A to ground and from point B to ground. So let's do it. We take our multimeter again, change here to the resistance mode, and we're gonna measure the resistance from point A. This is point A to ground. Let's get the proper range. The resistance measured from point A to ground is 58.8 ohms. So that's 58.8 ohms. Let's also measure the resistance from point B to ground. The ground is still the same place. This ground and here, this wire are together, connect together, so I don't need to disconnect that. So the resistance measured from point B to ground, called R prime TH, is 197.8 ohms. So R prime TH equal to 197.8 ohms. And I used the Thevenin theorem to combine these two Thevenin sources into one equivalent circuit and show the values in the. And step 9, use the superposition theorem to combine the two Thevenin sources, them, and into one equivalent circuit over here, and show the value of the single equivalent circuit on figure 6. What we need to do is similar to the previous part of the experiment. With VA subtract VB, that is 0 volt, 0 volt, and then we need to add two resistance. After adding RTH and R'TH, I get 256.6 ohm. This is the equivalent Thevenin resistance. And this is the single equivalent circuit of that figure 6. This is the end of the Wheatstone bridge experiment.